Hello, this is Itsu. Okay, this will be one of the first video chunks I made about this pulse motor sequence circuit designed by Verpies. I will show you the layout, and in some further video links or chunks I will show you the signals generated by it and some calculations. We can later on put in a spreadsheet and pie chart also created by Verpies to see how the energy balance is in this pulse motor. This circuit is the latest with some changes because of some leaky Zener diodes which did not perform quite as it should be, so we had to add some extra MOSFETs. But basically this is the layout and this is the circuit. It's kind of mirrored compared to the diagram, but that's not that important. Below the four 4047s we have the big 10 microfarad C2 cap, which will be used to capture the flyback. We have the MOSFETs Q1, Q3, Q4 and Q5. We have the L2 choke and the CSR, the flyback diode to capture the flyback, L1 coil and the rotor. Some additions here are the 555 timer, which I can use to as input for the 4047 stream. I have another input from my function generator via a optocoupler, which via this switch I can select either the 555 timer or the function generator as input for the 4047 stream, which will be here. And the purpose is that during the measurements I have to make some scope probe settings where the ground leads of the scope are being on the 12 volt rail, so we cannot have then a function generator hooked up, so it's isolated, or we use the internal 555 timer. Okay, so next I will show you some signals coming from the function generator fed into the 4047 streams to see how it can manipulate the input to the Q1 MOSFET and the Q4, 5 and 3, which shorts out the big capacitor. Okay, here I have put some probes on some key points. The yellow probe is on the input of the first 4047, which would be here, the incoming signal from the function generator via the optocoupler. I put the function generator at 40 Hz, 2 volts, all positive, 20% duty cycle, and behind the optocoupler and via the switch it's fed to this first chip, and we can see here the signal 40 Hz, 10 volts, 11 volts almost, 20% duty cycle. After this input the signal goes either to Q1 or goes through to the 3, 4, 5 shorting MOSFETs. The first signal we can manipulate is the gate of Q1, which times the rotor, and the signal I've put up is the blue trace, which at the moment is similar as the input signal, but with the two pots. The first two I can manipulate the position and the width of this pulse, like I will do now. We can move this pulse compared to the input pulse to position it at the correct position very smoothly, and we can change the width of this pulse also by moving the width voltmeter. But we like to have it the same as the input, which is 40 Hz, and the correct position here, and about 20% duty cycle. Okay, the second two 4047s manipulate this pulse to get a subtiming for the shortening, which I have put up the gate of Q4 and 5. And we can see we have a negative kind of pulse, which I can also manipulate both the position, if I can do that with one hand without disrupting everything. We can move it compared to the blue signal, which is the Q1 L1, and we can manipulate the width also of this pulse with the other pot. So we have full control very smoothly about the signals to the several MOSFETs. Okay, next thing I will hook up the probes again on a different way to show you the timing in a working fashion. Okay, I put some probes on some other points and have the rotor running. It takes a lot of kinetic energy from myself to have this rotor synced up at this 40 Hz speed, so there's a lot of input for me to get this rotor running. All the circuit does is tapping at the right moment to keep it running. I have the multimeter across the C2 cap, and we can monitor the RMS value, almost 40 volts. The four probes, as can be seen here, the blue is across the CSR, which is between points A and B, and the ground is at this point, at the B point, meaning it's at almost 12 volts. That's for all the other measurement points, so that's the reason why we have the function generator isolated with the optocoupler. So basically the blue trace is the voltage across the CSR. It's at 0.1 ohm, 1% CSR. So we have this value times 10 milliamps running through the coil. The purple trace is the drain of Q1, which powers the L1, which powers the rotor. And we can see the on time when the signal goes down, and afterwards we see the flyback spike from the L1 coil, which is the one we want to collect Yellow trace is the voltage across the C1, the big red capacitor, which we use to capture this flyback. So we see here that it's already filled from the earlier cycle. At this moment we short it out with the shorting MOSFETs until it reaches 0 level, and then we fill it up with the spike again, with the flyback spike. So this is the value from the flyback spike, and we keep it until the next cycle, and just before the next flyback we short it out, and then it's now kind of wasted because we short it out, but we can do several things with it, like moving it to another cap, moving it into a battery, or put it back into the run battery or whatever, but that's for later. The green trace is the moment we can short this capacitor before the flyback, and with the last two pots we can adjust the position. Let me try to show the position of this pulse before it gets shorted. We try to keep it as short as possible before the flyback, and we can also adjust the width of this pulse, which we need, otherwise the signal will not go fully to 0, the yellow signal, so we need a certain timing. Okay, this way the RMS value on the yellow trace will be the same as on the DDM, almost 40 volts. So that's the key point. So next chunk of video I will make to try to calculate the input wattage and the time for the flyback, and this data we need we can fill in the spreadsheet, and to see some visual representation of the power used in this circuit. Okay, last set of this video is making some measurements for the input, so we can fill the spreadsheet with valid data. So I have again changed some probe settings. We have the blue trace is again the CSR, measuring the current into the L1 coil. I have the yellow trace is the voltage of the battery, 12.6 volts at the moment, and the red trace is the MAT functions, blue current times yellow voltage, and we have the wattage there. I only measure in the on time, which is between the two purple vertical bars. So I only measure the power in the on time. We have something like 41 milliamps taken times 10 because of the 0.1 ohm resistor. It's 410 milliamps RMS. We have 12.5 volts from the battery RMS, so the calculations are 4.62 milliwatts times 10 is almost 4.6 watts input. So we can note this down. Also we have to take note of the on-time duration, which is also mentioned here, 4.98 milliseconds. And another set of calculations needs to be taken of the flyback pulse, so we move this cursor so we can measure the duration of the flyback. Which is 1.04 milliseconds, and the RMS value of this flyback is 41 milliamps times 10, and also the main is important. We can note this down. So with this data we can fill in the spreadsheet and we can see what the energy balance is of this circuit while running. Okay. Big thanks to Verpis for designing and helping flatten out the bugs and stuff. And as always, thank you for watching.